Time. I'm not going to give you a precise definition of time. Physicists would define time as the direction in which entropy increases, but that doesn't mean much to very many people. We all have a kind of a feel for what time is. It just keeps going. You can't turn back the hands of time, it would seem. And it's something that's measurable, but it's kind of hard to put a real definition to. The SI unit of time is the same as the English unit of time, and it is the second. Of course, there's a real precise definition for what a second is that people who measure time very carefully have to use. It's 9,192,631,700 times the amount of time it takes for one cesium atom to oscillate once. That's not very practical. Most of us, we can get by with a stopwatch, the little quartz oscillation in a stopwatch, or even just watching the second hand on a clock. Be good enough. Here's time placed in our background of our universe. The estimated age of the universe, based on scientists' best efforts here, is 10 to the 17th seconds. So that's a lot of seconds. Here's a teenager. Typical teenager would have a lifetime of about 10 to the 8th seconds. The time it takes for the Earth to go around once, in other words, a year is 10 to the 7th seconds. So teenager would be a number of years, and so it would be another order of magnitude, 10 to the 8th. A day, one calendar day here represented by this little picture, a day is 10 to the 4th seconds. So that's on the order of 10,000ths of seconds. Human heartbeat, from start to finish, human heartbeat is on the order of about 1 second. Sound waves are going to be, they're going to be these fluctuations that are going to be roughly happening about every 10 to the negative third seconds, or every thousandth of a second, roughly. We can actually hear from 20 vibrations a second up to about 20,000 vibrations a second. So that's a fairly wide range. This is sort of in the middle of that range, about a thousandth of a second. Anything that can vibrate that fast, we can hear. This is supposed to represent radio waves. If this is your signal that represents the voice or the music, this is how we'd modulate that on what's called AM radio waves, and this would be what we'd modulate on FM radio waves. You can see that how often the vibrations occur is much more rapid. It's much more high frequency for AM or FM than it is for the radio waves. And radio waves are going to have about 10 to the negative 6th seconds for their frequency. So that means about a millionth of a second. Every millionth of a second, there's a new wave front coming out from a radio station. This is we're supposed to represent light waves here, and the frequency of things that vibrate that are going to produce visible light, like blue light in this case, would be on the order of about 10 to the negative 15th seconds, about a femtosecond, which is, you think about every 10 to the 9th being a billion. This is nearly a billionth of a second that frequency for vibrations that cause light waves is occurring. Another thing that we measure from time to time, not as much maybe in physics as in some other sciences, but it shows up in physics, is temperature. Temperature is really an ability of energy to flow through a process that we call heating. Heat can move from one place to another if there's a difference in temperature. So if you want to know, is your house going to cool down or is it going to heat up today, you'd have to know what's the temperature in the house, what's the temperature outside, and if they're different, the energy is going to flow from the hot place to the cold place. That's what temperature is all about. The English unit is the Fahrenheit, 1 degree Fahrenheit. And we measure all kinds of stuff in degrees Fahrenheit in this country, but we're about the only ones. Typical room temperature, about 68 to 72 or so Fahrenheit. human body temperature is 98.6 Fahrenheit. Good hot day is, 100 or so, a little hotter in desert climates. Cold day would be, below 30 degrees or so. That's the English system that we're familiar with. In the SI system, there's actually kind of a split here. Scientists are going to prefer what's called the Kelvin. And the Kelvin is abbreviated with the capital K. And if we think about going back to the English unit, if you think about an English thermometer, Fahrenheit thermometer, boiling point of water is 212 degrees Fahrenheit on that system, and the melting point, or the freezing point, same temperature, of water is 0 degrees Fahrenheit. So the distance between there is, I'm sorry, it's not 0 degrees Fahrenheit, it's 32 Fahrenheit. So the distance between here is 180 degrees. So 1 Fahrenheit degree is 1/180th of the difference between the melting point and the boiling point of water. Not a convenient unit, as is typical of the English system. In the SI system, this is 1/100th of that same distance. So if you have boiling point water and you have melting point water, that temperature difference is divided into 100 segments, a much easier number to work with. And so we have 1/100th of that distance. And that represents both the Celsius degree, which most people have some familiarity with. It's used by most of the world to measure temperature. And the Kelvin is actually the same size of a degree. Kelvins are used by scientists. Celsius is used by lots of other people. And there's a reason for this. It has to do with calculations and simplifying some calculations. We'll talk more about that later. In Celsius versus Kelvin, the only thing that's really different is where do the degrees start. A Celsius thermometer, draw a picture of a thermometer here. Celsius thermometer, there are two important measurements, 0 and 100. This is boiling point water, this is melting point water. However, you can go below 0, and that presents some calculation problems in many situations. So in the Kelvin scale, 0 is actually way down here. 0 is the coldest conceivable temperature that there is. There are several good experiments that have given us a reason to believe we know what that temperature is, and that should be, in the Celsius scale, about negative 273.15 degrees Celsius. Well, that's where Kelvin starts. So negative 273.15 Celsius, that's 0 in Kelvin, which makes 0 273.15, and it makes 100, or the boiling point of water, 373.15, because the size of a degree in Celsius and Kelvin are the same. So to convert, you can just quickly add. That's all you have to do. Converting temperature units, Celsius to Kelvin, you take your degrees C and you add 273.15. And a lot of times we'll just drop the 0.15 and round it off. And that will give you a temperature in Kelvin. Converting from Celsius to Fahrenheit is a little trickier, and that's because we've got two different size scales. There's actually a linear relationship between the two. And if you ever get stuck, you can work this out. If I were to graph degrees C on this axis and degrees Fahrenheit on this axis, when I'm at 0 degrees C, I'm actually at 32 Fahrenheit. And when I'm at 100, I'm at 212. There we go, 212 in Fahrenheit. So this makes a straight line. There are 2 points determine a line. I can draw a straight line between that. The slope of this line is 180 over 100, or 9 over 5. And so that means if I take 9/5, that's the slope of the line, times the temperature in degrees Celsius, and then my y-intercept is 32, I add 32 to it, well, that gives me my temperature in Fahrenheit degrees. So there's a conversion factor that allows you to convert Celsius to Fahrenheit. You can just do a little algebra on this equation and you can get the Fahrenheit to Celsius. Just ends up being this. Fahrenheit temperature minus 32 that whole quantity times 5/9. That will give you the Celsius temperature. So you should be starting your toolbox now of equations and stuff. This can go in your toolbox. This is an equation that will allow you to go back and forth between the two systems. Well, we've reached the end. If you haven't figured this out, I'll give you the answers. Most famous female physicist probably ever, Marie Curie. She is standing out here in some kind of apparently fairly cold conditions with the most famous male scientist probably who ever lived, and that's Albert Einstein. They're talking about something important. Albert looks like he's smoking a pipe. They both look like they're shivering. Well, that's it. More tools to follow later.